you need to know how to graph the logarithmic function. So if you don't know how to graph the logarithmic function, or you get confused with transformations, asymptotes, domain, range, natural log, and log with different bases, then please go through this video and watch the examples as I show you from my best examples of teaching inside the classroom how to graph logarithmic equations. I hope you enjoy. So in this equation, we have y times a times log base b of x. And again, I'm just going to show you just a general example. Let's do y equals log base 2 of x. All right. And if you guys can see, if you remember your conversion between exponential and logarithmic, basically what this is saying is b raised to what power gives you y. So this is basically saying 2 raised to what power is going to give us x. That's what that logarithm says. And we'll practice more of this later. But the important thing that I want to understand here, or for you guys to understand, is if we have x, y, for exponential, there was no problem with plugging in anything in for x, right? There's no problem with plugging anything x. And you guys can see the domain is negative infinity to infinity. However, the logarithmic function has a little issue, because what this is saying is 2 raised to what power gives you x? Well, the issue is if x is negative, like think of a number where this is going to give you any kind of negative number. So what the problem is that there is no number that exists where you can take 2, raise it to a power that's going to give you any negative number. Doesn't matter if it's negative 2. Try to think of numbers. You could think of 1. Nope, that gives you positive 2. Think of negative 1. Nope, that gives you 1/2. Right? So it's impossible in our number system to be able to choose a real number x that's going to give you a negative number. Okay? So, I guess I could show you on Desmos. Actually, we'll break out Desmos. So anyways, when you're looking at this, we cannot choose any negative numbers. So we're just going to choose 0, 2, and 4. And I'll explain to you again why I'm choosing these values. So again, when we're looking to identify the table, basically this is saying log base 2 raised to 0. So 2, what this is asking is log base 2, actually let's do it over here. Y equals log base 2 of 0. Again, the logarithm, what it's stating is 2 raised to what number is going to give you this y. So 2 raised to what number is going to give you 0? And that answer is, 2 raised to what number gives you 0? We don't have that. That's undefined. Sorry, that's supposed to be 1. 2 raised to what value is going to give you 1? And I'll explain. We'll look at this in a second. That's 0. Y equals log base 2 of 2. Again, the logarithm is asking 2 raised to what power gives you 2? 1. And then last but not least, log base 2 of 4. 2 raised to what power gives you 4? 2. So if we were to graph this, it's impossible, again, if you guys look at that, to have 2 raised to a number to give you 0. Think about that. What could you raise to a power to give you 0? Nothing. I mean, 2 raised to the 0 power is 1. So we're kind of at a loss here. So that's why that's undefined, which you guys will see in a second. So if we go to 1, 0, if we go to 2, 1, 1, 2, 1, and then we go to 4, 2, 1, 2, 3, 4, up 2. And what you'll see is you're going to have a function that's going to look like this. So therefore, our domain is from 0 to infinity, and our range is from negative infinity to infinity.
All right, you hate asymptotes. What did asymptotes ever do to you? Your asymptote. Okay. So if we're looking at a logarithmic function, one thing we talked about was when we're looking at just the general, right? I told you guys in your outlines to make sure you guys have this written down. Our general form of what our graph looks like. All right? And one thing you guys looked at is the graph is always going to cross at 1, 0. And it's going to look something like this. Okay, well here we know our x-intercept is at 1, all right, and then our domain was equal to 0, comma, infinity, right? It goes from 0 to infinity. Our domain is never in the negative, and our vertical asymptote was when x is equal to 0. All right, so that was part of your guys' outline. That should have been on there. You should have had this in your outline, nice and written up there, so you can always remember it. Because remember when we talk about transformations, you have to know what your parent graph looks like to shift it up, down, left, right, and all that kind of stuff, right? Yes?
So the domain would be 0 over? Wouldn't it be greater than that? Or that's the same?
Your domain is all numbers greater than 0.
Always?
Okay. And when we get into a problem that's going to have a different x, I'll explain a little bit this. But yes, you could say your domain is like all values, which we're going to talk about, like greater than 0. Which we'll talk about that in a second. So, anyways, if I want to find the domain of this function, right? This was for log base a of x, where a is going to be any base. It doesn't really matter what your base is. It's going to affect a little bit of the, it's going to affect the change of the shape. However, your domain, vertical asymptote, and your intercept are always going to remain the same. So your base is not going to affect this information. So when I look over here at this graph, do I have any transformations? Do I have any plus, minuses, shift, left, right, no reflections, right? Nothing. So therefore, I can just say, hey, my domain is going to be 0, infinity, and my vertical asymptote is equal to x equals 0. So nothing changed. All right? Then let's talk about x-intercepts. And let's go back to, yes.
Said the y equals 0.
Yes. I want to go back to algebra 1. Maybe give you guys a little bit of some happy thoughts. Maybe? No? Let's say y equals, I don't know, let's call this like a negative x plus 3. Right? And if I want to say what is the x-intercept, where does the graph cross right there? Well, what we said was that's the x and that's the x-axis. Here's my y-axis. The y value at this point is when y equals 0, right? So you'd say 0 equals a negative x plus 3. So you subtract 3, divide by negative x, you got x equals a positive 3, right? That's how you found the x-intercept. You plugged 0 in for y, right? Then, if you're looking at, remember we did quadratics, we say, hey, what was the x-intercept? The x-intercept is when y equals 0. Both at these 2 points, the y value is 0, right? Okay, so when we talked about rational expressions, what did we do? We plugged in 0 in for y, right? And then we had to multiply the denominator of the rational expression on both sides, cancel that out. So whenever you're trying to find the x-intercept, y equals 0. So our function, we don't have a y, we have an f of x. Well, remember, f of x and y are kind of interchangeable. We're using functions because we're talking about functions, but your y is your output, it's the same thing. I could also write f of x equals 0. It's your output function, output value equals 0. So I say 0 equals log base 4 of x. So then, you're supposed to solve your x-intercept with this, right? Well, if you guys looked at our notes, I went over one problem like this, but I didn't explain how to solve for logs, right? All we did was we showed, hey, logarithmic to exponential. And that's all we did, logarithmic to exponential. So you got to look at your homework and think, well, all right, what is the only things that we possibly went over? Well, I don't know how to solve this for logs, right? If it was addition and subtraction, it'd be easy. You just add, subtract, you undo addition and subtraction to get your answer. Well, the logs, how am I going to get rid of this log? The only way to get rid of the log is we can transform it to exponential form. So we can write this as 4 raised to the 0 power equals x. And remember, anything raised to the 0 power equals 1. So therefore, x equals 1. So my x-intercept is 1, which obviously, since we didn't move the graph left or right, you guys should have known that the x-intercept was still going to be 1, right? Which is pretty basic.
I thought it was 3.
Where'd you get 3 in this one?
For the x-intercepts, that's what you just did, like the second one.
No, that was just a little sidebar that I had up there. Yes.
So that's why I said like the base doesn't matter because it's always gonna be the 0.
Right, yeah, exactly. The base is, it doesn't matter if I put E, 100, 3000, it's always going to be raised to the 0 power, so it's going to equal 1 when you have transformation. Cool? Yes?
Can you do the one that happened?
Yep, I will. I'm just going to shut off the video now, so then I'll do one of those problems.
Welcome. So here we go. Now I have a y equals negative log base 6 of x. So now we're starting to create in some transformations, and we see, when we have a this is not a function, it's an equation, but whenever we're taking our family of functions, we're multiplying our function by a negative value, we know that this is going to be a reflection of the x-axis. So when I'm completing these problems, and whenever I see transformations, I always like to write them out so I don't forget them. So let's go and look at a general parent graph. And then we'll see what the graph is going to do. So the general parent graph of a logarithmic equation with any base, we know that's going to have a x-intercept at 1, 0. And it's going to look something like this, where my asymptote is going to be at x equals 0. My domain is from 0 to infinity. And my range is going to be from negative infinity to infinity. However, now you can see that I have a base 6. So I want to see, what is this base going to affect my graph? So to do that, we always can graph functions and equations by using a set of values. And what I always like to do is rewrite this in exponential form. And what I'm going to do is, without my transformation, so without that reflection, I'm going to rewrite it in exponential form. So therefore, it would be 6 to the y equals x. And I'll explain why I'm not going to deal with my reflection when I'm finding the coordinate points. Because what I want to do is I want to find the parent graph, then I want to apply the transformations. So it's really important when you're graphing this to graph what the parent graph is going to be and then apply the transformations. So if I use the exponential equation 6 to the y equals x, I'm going to have some coordinate points I'm going to want to graph. So I just create a table of values. And when I'm graphing, I just want to choose kind of 2 points. And the best 2 points that I always like to use is when x equals 1 and when x equals my base. Sometimes we can, when x equals whatever my base can be. So when looking at this, if I have 6 raised to the y is equal to 1, so 6 raised to what power is going to equal 1? Well, we know that y is going to equal 0. And why do I write that? That's supposed to be a 6, right? That's the base. So my base is 6. So 6 raised to what power equals 6? That answer we know is going to be 1. So now I can plot these 2 points as my parent graph. So I have 1, 0. And I have 6, 1, 2, 3, 4, 5, 6, 1. So my graph, my parent graph, looks something like this, right? But now what we're going to do is we're going to apply the reflection. So ladies and gentlemen, if we're going to take this reflection, what we're going to do is we're going to reflect it over the x-axis. So if you look at a general reflection over the x-axis, it's going to look something like that, right? You're taking your graph and you're reflecting it over the x-axis. So my coordinate point at 1, 0 is still going to remain the same. But now my point 6, positive 1 is now going to turn over 6, negative 1. Then we can just simply take our eraser and just erase the original parent graph. And there, now we have graphed it with 2 points, 1, 0 and 6, negative 1. And now we can go and look at our asymptote. Well, my asymptote hasn't shifted at all. So my asymptote is still going to be at x equals 0. My domain, you can see, is my graph is still going to be from 0 to infinity. I don't have any negative values for my domain. And my range is still going to go all the way up and then all the way down. So therefore, my range will still be from negative infinity to positive infinity. So there you go, ladies and gentlemen. That is how you graph a logarithmic equation. Thanks. Welcome. All right, so here we go. We have y equals ln of x raised to the 5th. And a lot of students hate natural logarithms because they just don't see that base. And they say, and they know the base is e, or sometimes they forget the base e. But then they're like, what does this number e represent? And I have a video for e, to go through. But the main important thing you just need to understand when we're dealing with natural logarithmic equations that our base is going to be e. But it's always going to be e for natural logarithms. So we're not always going to write it out. Now I look at this and I see that there's no transformations, but I have my variable being divided by 5, which is very odd in comparison to some of the problems that we've been going through. So if I was going to graph this, again, what I would do is I'd just set up an xy coordinate, and then I'd set up an xy table. Now, just like I've done for my other problems, I am going to take my parent graph, y equals ln of x to the fifth, and I'm going to rewrite it in exponential form. So there would be e to the y equals e to the y equals x over 5. Now, ladies and gentlemen, when we're dealing with e, it's going to be a little bit more difficult than just saying, oh, you know, I want to have these integers, because we understand e is an irrational number. So I could multiply by 5, and therefore my x values are going to equal 5 times e to the y. All right? And so when we're looking at this, you know, it kind of gets a little crazy. We're just going to want to choose some values, and then we're just going to approximate those values as best we can, to be able to at least set up some graphs. Now, there is one point that we can always choose that's going to be the best, is when our x is going to equal at least what our base is. And what you can see is if I had y equal to 0, right, then that would be e to the 0, which would be 1. 1 times 5 would just be 5. So therefore, I know when x equals 5, remember I always said what our base is, and we can eliminate with that e to the 0 when when y equals 0. So I know I have one coordinate point, which is 5, 0. But there's another kind of point that I need to be able to figure out of what it's going to look like. So 5, 0, 1, 2, 3, 4, 5. But now I need to go ahead and determine, you know, what else, what other point can I go ahead and use for there. And, you know, you can just pick any real point that you want to. We don't need to get crazy. And you can just plug it into the equation. What about, let's just try x equals 1. And how about we try when x equals 7? All right, and again, we're just going to be approximating these points in my equation. So what I'll do is, I'll just actually just take my equation. I'll take ln of, let's do 1/5. So ln of 1/5 is going to be negative 1.61. If I do ln of 7 over 5, and I get ln of 0.366. So therefore, when x equals 1, I have negative 1.61. So let's say that's 1. That'd be 2. And then when x equals 7, I'm at 0.366. So 1, 2, 3, 4, 5, 6, 7. So you can see this graph is going to have a very, very sharp turn, and it's going to have an x-intercept at 5, 0. Not always at the x-intercept at 1, 0, and the reason why is because we're multiplying it by this value of 5, okay? And that's what, you know, when it comes into that value, x divided by 5, what that's doing is actually expanding that graph. So therefore, now I'm going to have a new x-intercept. However, let's go and take a look at now, how is my asymptote and everything else going to change? Well, my asymptote is still going to be at x equals 0. My domain is still going to be from 0 to infinity. And my range is still going to be at negative infinity to infinity. The only thing that changed is now my my x-intercept has now changed by it's been shifted over because the graph has expanded out. So there you go, ladies and gentlemen. That is how you graph a natural logarithmic equation. Thanks. OK, so what I have here is y equals 1/3 to the negative x. And I figured this would probably be a good problem to go through because we see a fraction. Everybody's like, fraction. Nobody likes fractions, right? But that's OK. Let's go through the problem. So I've showed you a lot of times, you know, with this, ladies and gentlemen, dealing with our parent graph. And our parent graph was just for any general base. We knew that without a general base and transformations, we knew that we had that x-intercept at 1 equals 0. But now we have a new base of 1/3, and we also have a negative x inside of our function. Now, I know I have an equation up there, but if we're dealing about a family of functions, when we're multiplying by a negative inside the function, we know that that's going to be a reflection about the y-axis. So a lot of times I like to write down that transformation. All right, so now the next step, what I want to do is graph just the parent graph with the base with no transformations. So therefore, I'm going to want to graph y equals log of 1/3 raised to the x. Forget about the negative, because that's a transformations. We'll apply that next. So what I want to do to graph this is I want to rewrite this in exponential form. So therefore, I can create a table of values. I'm sorry, that's written wrong. That's 3 to the y equals x. So by creating a table of values, when graphing a logarithmic equation, you could obviously create a whole bunch of table of values if you want to, and graphic technology will work for that. But since I'm just making a video with no calculator, I'm going to only do 2 points, and I'm going to make them kind of simple. So the 2 points that I always like to use is what's going to be my base, which in this case would be when x equals 1/3. And then also I want to make sure what is going to be my base when it is equal to 1. So if I have 1/3 raised to what power is going to equal when x equals 1/3, we know y is going to have to be 1. And 1/3 raised to what power is going to leave me with 1, we will y is going to be 0. So now what I can do is I can just graph these 2 points. So I graph the point. So I graph the point 1/3 up 1, and then I graph 1, 0. Yeah. OK. Then what I'm going to look at is you can see that this graph, as I see this is now being written as a thing. So this graph I was going to follow along is going to take a form looking like this, right? So now I go ahead and apply my transformations. Well, instead of going over 1/3 up 1, by applying this transformation, I'm going to reflect this over the y-axis. Therefore, my 2 new points are going to be left 1/3 up 1 and left 1, 0. All right. So then now what I can do is I can go ahead and just erase my original kind of parent graph with no transformations. And that is now just going to leave me with my graph with a reflection over the y-axis and a base of 1/3. Thanks. OK. So ladies and gentlemen, what I'm going to do is show you how to graph y equals 2 ln of negative x. So again, I look at my transformations. And since I'm multiplying by a negative number inside of my natural logarithm, I am going to reflect about the y-axis. All right? So the first thing, though, I want to do is graph my logarithm with no transformations. And then I'll actually graph it with the transformation. All right, or with at least the reflection we have here. So the first thing is I want to go ahead and determine these values that I'm going to have. And to do that, when you're dealing with natural logarithms, remember, you know you have a base e, right? So a lot of times when I was converting them to exponential form, it was very basic. But when we're doing with e with an irrational number, you can't really do so many in your head that's going to work. So I still can create a table, though. And if I was going to create a table, and actually, you know what? I could even, yeah. If we approximated e as 2.72, even though it is irrational, there's a couple points that I could pick without I have to go through all these different equations. So one thing I could do is, if I could pick my value of 1, and if I have ln of 1, we know that that is going to equal, ln of 0. Ln of 0 we know equals 1 because ln of 1, that's right, ln of 1 equals 0 because here we have e raised to the 0 equals 1, right? OK. So if I put a 1 in for x, right, we know ln e raised to what power gives you 1? Well, that's going to be 0. So therefore, ln base e of 1, so if I was going to do 2, so if I said y equals 2 times ln of 1, ln of 1 we know is 0. 0 times 2 is just going to be 0. So therefore, y equals 0. when x equals 1. Hence, given our x-intercept at 1, 0. Yes? Yes. Then another one we could say is, what about if x equals e? So if I said 2 equals 2 times ln of e. Well, e raised to the e power is just going to be 1. 1 times 2 is 2. So when x equals e, y equals 2. So I could go up to 2. Now remember, e is approximately 2.72. That's approximate. It's an irrational number. It goes on and on. So at, let's see, 1, 2, 3, 4. So at 2.72, so 2.72, I know y equals 2. All right, so my graph's going to look something like that. All right, pretty rough estimate here because I'm approximating this point, which is e, comma 2, or what I'll do is 2.72 approximate, comma 2. All right, so that's now what my parent graph is. And now what I need to do is reflect this about the y-axis. So instead of my points now being positive, then now I'm going to take this graph and reflect it over the y-axis. So when I go ahead and graph this now on an xy coordinate axis, instead of going over 1, I'm now going to go to the left 1. And instead of going over 2.72, I'm now going to go to the left 2.72 up 2. All right, and what's very nice about this is you can see over here, my asymptote is at x equals 0. My domain is all positive numbers, so it's going to be from 0 to infinity. And my range is from negative infinity to infinity. Well, when I reflect the graph over the y-axis, you can see now my domain is all negative numbers. So my domain now is from negative infinity to 0. My asymptote did not change. Just because I reflected over the y-axis, my asymptote is still going to remain the same, which is x equals 0. And my range has not changed either. That will be from negative infinity to infinity. So there you go, ladies and gentlemen. That is how you graph a natural logarithmic equation with a reflection about the y-axis. Thanks. All right, so here we go. Next equation I'd like to write is going to be a y equals ln of x minus 2. So I'd like to go and show you how to graph this. And what we're going to do is we're going to apply some transformations. So the first thing I like to do is, first determine exactly what our transformation is. And since we're subtracting the 2 inside of our function, we're going to shift the graph 2 units to the right. All right. Now, so we're going to shift it 2 units to the right. And what we'd like to do is maybe kind of determine exactly what does the logarithmic graph look like without, or a natural logarithmic graph look like without any transformations. Now remember, when we're dealing with natural logarithms, we have a base e. All right? So if I was going to take a look at this, I can just kind of plot some points and kind of see what exactly I'm going to have here. And you can transfer these over into exponential form, but usually with logarithmic graphs, it's not going to be necessary. We know that the graph is going to cross at 1, 0 unless it's being multiplied by a multiplier. And it's going to look something like this. All right? And we can go and test that by putting in 1 in for x and then determining the value. And then usually what I like to do is just pick another point, 2 or 3 or something, just to kind of see where the graph is going. So since I don't have any other since I don't have any dilations, nothing's being multiplied by my ln of x, what I'm going to do is just take ln of x and just create a table with it. So let's do ln when x equals 1. Well, therefore, my y is going to equal 0, hence how I already knew that 1, 0 was my point. Now let's go and do just like ln maybe of 5. Now this is going to be an irrational number. All right, so I'm just going to approximate it to the 10th, so 1.61. So over at 5, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, I'm going to be up at 5, 1.61. All right, and again, that's a approximation because it's going to be irrational, not that exact point. However, what I notice is I'm going to be shifting my graph 2 units to the right. So that's not going to affect my y values, but it is going to affect my x values. So now, instead of the graph crossing at 1, 0, it's now going to cross at 1, 2, 3, 0. And instead of the graph having another point at 5, 1.61, it's now going to have a point at 7, 1.61. So 1, 2, 3, 4, 5, 6, 7, and then 1.61, which would be over there. So I like to plot these points, so just write them out there, 3, 0, and then 7, 1.61. And the next thing that's also important is when we look at our general graph, we need to determine again what the asymptote is, domain, and range. So the asymptote of my parent graph of a natural logarithm is x equals 0. And where the domain is from 0 to infinity, and the range is from -infinity to infinity, right? Because you can see the domain is the set of all x values that are going to make this equation true. We don't have any x, we don't have this graph crossing over 0 into the negative values, so my domain is only contained from values that are going to be positive. However, the range, this graph decreases and also increases to infinity and -infinity, so therefore the range is going to be all real numbers. Well, now I've shifted the graph 2 units to the right. So now my asymptote has now changed to 2. And remember, the asymptote is where your graph is going to approach. So my graph is going to be approaching 2, but it's not going to cross it or touch it. So therefore, our graph's going to look something like this. So there you go, ladies and gentlemen. That's how you graph natural logarithm equation with transformation. Thanks.
So here what I have is now I have an x plus 2, which is going to tell me I'm going to be shifting my graph left, right? Because it's inside of my function. So you guys can look at the graph and say, all right, if my x-intercept is at 1, 0, now it's going to be shifting left 2, right? So my graph now is really going to look something like this. Or I'll just make this the dotted parent graph. Right? So how can I go ahead and do this without actually knowing? Now that's pretty simple, right? But let's go and take a look at how can I algebraically show my work so that Mr. McLogan can see exactly I know what I'm doing. So if we say my domain is 0 to infinity, what we're saying is all x values are greater than 0, right? Well, that's for the function of log, base 10 of x. Well, what we're going to do is now, to kind of just show exactly what your domain is, what you can say is take what's inside of your function and set that greater than 0. So say x plus 2 is greater than 0. Then solve for x. And if you guys remember doing the domain for a radical?
Would that be a -2? Yeah.
Yeah. Do you guys remember doing the radical? Remember when we did domain? I said set what's inside of under the radical, set that greater than 0. You guys remember that? Greater than or equal to 0? This is kind of the same thing. You're going to take what's inside of your function and set that greater than 0, because that's your domain. Your domain is all x values greater than 0. So if you're changing anything inside of your function, set that equal to 0. Or I'm sorry, greater than 0. The same thing, so this is for your domain. Same thing for your vertical asymptote. Your vertical asymptote on this is x equals 0. Well, that was for your parent graph up there. So if you want to find out what is my new what is my new vertical asymptote going to be, do x plus 2 equals 0. So now x equals a -2. Which, you guys can see, that's 1, that's 2. Really kind of makes sense because what am I only doing with my graph? I'm just shifting it to the left 2, right? So this is an algebraic way to show that your domain is now going to be from -2 to infinity. And your vertical asymptote is when x equals -2. Yes?
If you were subtracting the 2,
Then it'd be a +2. Because remember, you'd be shifting it to the right.
still to infinity?
Huh?
Still to infinity?
Huh?
Still to
Yeah, still to infinity. Yep, your graph is still going to be going to
But what if
the.
it was -1?
Well, then what would happen is if you had if you had that negative inside of there, then you'd have to divide, right? Divide by -1, and you'd have to flip the inequality sign.
How would you write that? Like, would you
It'd be the same like this. You'd have like a negative this, and then you'd have to divide. Do you see that? Is that? No. What are you talking? What are you asking?
How would you write the domain? Would it be like a negative and
or -2 to -3, or like if it was split, that +2 to
This is so lame.
-3.
I'm sorry, say that one more time.
Flipped it.
Right. If it was flipped, that means I'm going to have a negative x, right? I told you, just take whatever's inside of your function. So if that was a negative x, okay, then I would have negative x plus 2 is greater than 0. Does that make sense? So just take whatever's inside of there. And if Chase, you have a 3x, if this was a 3 inside of there, then it'd be 3x plus 2 is greater than 0. Just take what's inside of your function, or what is your function, and set it greater than 0.
How would you write it though?
Okay, well I have this, right? Then you have to solve for x. So here I would subtract 2. I get negative x is greater than 0. What am I dividing? Negative 2. I divide by negative 1. X is now less than 2. Right? So my domain, okay, would be from negative infinity, because it's all values less than, can you guys please be quiet? Less than 2, all the way up to 2. So that would be my domain.
Okay. But what if it was x minus 2, like I said prior? Without the negative x. There we go.
So it'd be x is greater than 2.
The sign wouldn't be flipped then.
Huh?
Why would the
Okay,
sign
but
be
then-
flipped?
No, you would only flip the signs if
You only flip the sign, yeah, when you multiply or divide
So
by
then how would you
negative.
write that?
So it says all values greater than 2. So your domain is from 2 to infinity.
All I wanted to know. The PP.
Oh, okay.
So, we're not dealing with an x. So going back from this problem, so if it was negative infinity, Jessica,
No.
if you have negative, you just go from it. It says x is greater than all values greater than negative 2, so it's negative 2. If I said x is greater than 2, you just go from 2 to infinity, right? Because look at the graph. Just look at what this graph's doing. It's still going to infinity. So you just pick the value that it's going to and then go to infinity.
Well, I just wanted to know, like, what if it was going to negative infinity, like how you would write it, so.
Well, if it was going to negative infinity, you'd see, remember, you'd have this whole graph would be flipped over, right? And you'd see that.
How would you graph it there and start at -2?
What would start at negative 2?
Like, is the domain, okay, is -2 to like infinity? How would you graph it? It's like.
Well, if the graph was from negative infinity to 2, this whole graph would be flipped over, right? And so what I really have is that I have now let's say my asymptote, that one was at -2, so now my graph would look something like this, because it'd be reflecting. All right. I don't want to get too off track, guys, because I have no problem answering questions. I'll answer them. I just want to finish up this video to finish up the problem, and then I'll answer more of your questions after that.
You're still meditating?
So yeah. So now the last thing I need to do, and that's not a problem, guys. I have no problem answering your questions and trying to get the most out of it. I just don't want to get too sidetracked. I want to at least finish up the problem. The last thing we need to do is find the y-intercept, or I'm sorry, the x-intercept. So the x-intercept is when y equals 0. So I say 0 equals log base 3 of x plus 2. So transfer this to exponential form. 3, 0 equals x plus 2. 3 raised to 0 is 1 equals x plus 2. Subtract 2, x equals a -1. And you guys can see when we just did that, that's where it crosses, x equals -1.
Why did you do that? Like,
We
I
did that
thought
to find the x-intercept.
No, I thought you had to subtract the 2 and then get -2 equals log 3x and then.
Not with
You
this
gotta
one because
transfer
they're
it to
inside the
exponential.
class.
You gotta transfer it to exponential form first before you can't. We haven't learned anything to get rid of that log. To get rid of the log, you gotta transfer to exponential
Oh,
form.
I'm not so small. Why did you move the 3 to the other? You can end these.
I didn't put a 3 to the other side. I transferred this to exponential form. 3 raised to the 0 power equals x plus 2. That is what we did, remember, in our warm-up. Transferred this to this. That's what we practiced today in the morning, right when we started class. We have this. It's going to go right there, right? And what we said was our domain is from 0 to infinity. and our vertical asymptote was when x equals 0. All right? Look up here, please. Please look up here. You guys need to see this. All right? That was your parent graph. Now, let's look at the transformation from this graph. All right? First of all, we need to look at this and say, okay, well, what is this 2 is doing what? It's just shifting it up or down, right? It's just going to be shifting my graph up or down. Is that going to change my domain left or right?
No.
No, right? Because remember, domain is dealing with x, your x values, right? So if I'm shifting my graph up or down, it doesn't matter what I do because your domain only deals with the value of your x values, right? Then the next one, let's look at this. This is telling me too, I'm going to actually do a reflection about the x-axis. So since I'm reflecting the x-axis, my graph is actually going to look like this. Again, does that affect my domain at all? No, the graph still is going to remain exactly pretty much the same as it's going to approach your x asymptote, and it's going to be going to infinity. So my domain for this problem is still going to be 0 to infinity. So you guys have to understand what your transformations are going to do to your parent graph. Obviously, if I had like an x plus 1 in parentheses and it's shifting my graph left or right, that's going to make a difference. But when it's just domain, when I'm just doing stuff up and down and reflecting about the x-axis, it's not going to change my domain. My vertical asymptote is still going to be x equals 0. So then the next point is we need to find the x-intercept. Yes. So if you remember from rational expressions, the x-intercept is when y equals 0. So what I'm going to do is I'm going to put 0 in for y. I'm going to say negative log base 3 of x plus 2. And then you're going to say, bull crap, Ms. McLogan, you never told us how to solve anything like this. And you're right, I haven't so far. Right? I've only taught you how to put it into exponential form to determine the transformations and what the parent graph looks like. So, and you guys should already know the x-intercept because we've been working on that all year. Well, you only have so many options you can do, right? We don't know how to solve for log, so let's do something that we at least learned. Let's transfer it to exponential form and see what it looks like. Does that kind of make sense? Right?
Wait, what are we trying to find here?
We're trying to find x. We're trying to find the x-intercept. So we put 0 in for y, right? Because remember the x-intercept? Where it crosses x, the 0 value is, or my y value is 0. So let's put it into exponential form and see what happens. So I get 3 raised to the 0 power. Oh, I'm sorry. Crap. Can't do that yet. This, we can't really put this to 0 power because we need to do something with this 2, right? So before I do that, I need to subtract a 2. So I get negative 2 equals negative log base 3 of x.
Isn't that the exponent?
What?
The x plus 2.
No, this isn't in parentheses. This is my log, and then it's plus 2. If it was in parentheses, yes, that'd be something different.
No, she's saying that your exponent.
Isn't x plus 2 your exponent?
No, my 2 is just adding to my function. I'm just adding the 2 to the function. It's not within the parentheses. I'll go over one where it's inside the parentheses. So then I need to get rid of my negative 1. I'll show you another example that I think what you're confusing it with. 2 equals log base 3 of x. So now it's in exponential, now it's in the logarithm form that I can transfer. So I'd say, remember what this says, a logarithm says 3 raised to what number gives you x? Well, to transfer to exponential form, I'd say 3 squared equals x. So therefore, my x-intercept is x equals 9. Does that make sense? Kind of? Not at all.
Then how is the parent graph? Your x-intercept is 1, 0.
Because remember, I didn't shift this up 2 yet. This graph, all I did was I showed you the reflection.
Oh, okay.
So remember, this graph, like this is just, me sketching it, but remember, you also have to shift, what this is, it's this graph shifted up 2. So it's gonna go like that, right? And like this, I just sketched your reflection so you'd see what the reflection looks like. But yes, the original graph would be, up 2 units. So it kind of looks something like this, it'd go like that. I mean, like I said, I'm just
Yeah,
roughly.
you confused me because you put it still at 1, 0.
Because what?
Because you still had it at the parent graph.
Yeah, I didn't graph it. I was just trying to find, because if you guys notice, I'm not making you guys do the graph. I just want you to find the domain, vertical asymptote, and your thing. All right?
So we have log of x plus 3. So adding 3, I'm adding it inside the parentheses. So you can say a horizontal. Horizontal shift 3 units left. Then the only other thing I'm doing is I'm subtracting a 2. But that 2, I'm not subtracting inside the parentheses. I'm subtracting outside the parentheses. So we can say that's a vertical shift 2 down. Does everybody see the difference there? Remember, horizontals are always that opposite direction. Now we need to sketch the graph. So we need to make sure we understand what the graph looks like. So we go back over, look at our notes, or look at what the graph that I have provided for you, and see that the logarithmic function looks like this. Has an x-intercept at 1, 0, and also has an asymptote at x equals 0. That's really, really important for us to remember. Really, really important. So that's the graph. You can see I'm going left 3. So 1, 2, 3, and then down 2. 1, 2. Now, if I'm shifting it left 3, the x-intercept moved left 3. But what else moved left 3? This vertical asymptote. So my graph should look something like that. Actually, let me do it in red. So the graph should look something like that. If you go around that way, please. Now, let's do the last one, is the domain and range. The domain. How far to the left is my graph going? How far to the left is going? -3. Is that included or not included? Well, not included. I put parentheses. But you guys see how this one, how it was included, right? Because there's a point there. There's no point there. It's an asymptote, so it's not included. And then it goes to infinity to the right. The range, how low does this graph go? How high is it going to go? Infinity. And there you go. Welcome. So, all right, ladies and gentlemen. So when I'm looking at a transformation, or when I'm looking at graphing a logarithmic equation or a logarithmic function, I always want to be able to determine exactly what my transformations are. So in this case, I have y equals 4 log base 2 of x minus 3. So we understand that we have an x minus 3. So by applying the transformations of a function, we know that the graph is going to shift 3 units to the right. All right, so that's going to be very helpful in understanding, how our graph is going to be shifting along. And this 4 and 2, that's going to just affect how the graph is going to be increasing or decreasing. So to graph this, what I'm going to do is I'm going to want to graph the parent function with no transformation. And then I'm going to want to graph the function with transformations. So to graph the parent function without transformations, I'm going to have y equals 4 log base 2 of x. All right. Now, to graph this, again, we can set up a table of values. So what I'll do is I'll divide. So I'll have y equals 4 log base 2 of x. Now, there's a couple properties of exponents we could use. Or you could also divide by 4 on both sides and then rewrite it in exponential form. So I have y over 4 equals log base 2 of x. Rewriting this in exponential form, we have 2 raised to the y 4th power equals x. So when I want to create a table of values, and remember, when I'm doing table of values for logarithmic equations, I just want to kind of pick 2 values. I don't need to get crazy. And usually my 2 favorite values are when x equals 1 and when y is going to equal, or when x equals the base of your exponent. So when x equals 1, we know that y has to be 0. And for x equal to be 2, we know that y has to equal 4. So now I can plot those 2 points. I have 1, 0. And then I have 2, 4. 2, 1, 2, 3, 4. All right, so you can see my exponential graph is going to look something like that, where my domain is still going to be from 0 to infinity. My range is going to be from negative infinity to infinity. And my asymptote, where my graph is going to approach, is still going to be at x equals 0. But now, ladies and gentlemen, I'm going to shift that graph to the right. So I plotted my 2 points, 2, 4. Now what I need to do is shift those points 2 units to the right. So to do that, if I had 1, 0, now shifting 3 units, to the right, is now going to be 1, 2, 3, 4, 0. And to take the graph, or to take the point 2, 4 and shift it 3 units to the right, I'm now going to have 5, 4. 1, 2, 3, 4, 5. So I have 4, 0, and now 5, 4. Then I go ahead and graph these. And the other thing is, remember, my asymptote was originally at x equals 0, but now if I shift that over 3 units, I'm now going to have a new asymptote at x equals 3. All right? And that makes a big difference as far as my domain, because now, when my asymptote was at 0, we know that all the values had to be at least positive. Well, now, all my values for my domain, my input values, have to be greater than 3. So as my asymptote now changes to x equals 3, my domain now changes from, instead of 0, it's from 3 to infinity. My range, though, however, is unchanged, so it would be negative infinity to infinity. So there you go, ladies and gentlemen. That is how you graph with a horizontal transformation. Thanks. Welcome. So, all right, ladies and gentlemen, what we have is we have y equals negative 2 ln of x plus 4. And we need to graph this. And to graph this, we want to be able to identify the transformations. So you can see I have a plus 4, and I put that x in brackets or parentheses so we know that we're adding the 4 outside of the function. So therefore, that's going to tell us to shift 4 units up. Then I'm multiplying by negative 2, and that negative is going to tell me to reflect the x-axis. Right? Perfect. OK, so now what we need to do this, though, we need to graph our parent function. And the parent function is with no transformations, y equals ln of x. Y equals 2 ln of x. And then we are going to graph our final function with the transformation. All right. So the first thing is we need to create a table to graph this. All right. And again, I just like to make this very simple. I like to go ahead and determine, what are going to be my values. If I plug a 1 in for x, ln of x is equal to 0. 0 times 2 is just going to equal 0. So my graph is still going to cross at 1, 0. And then I can just pick, really any point that I want to. If I don't know, let's just pick 3. So if I do ln 2 times ln of 3 to find the value, I'll plug it into my calculator. And I get 2.197 ... It's going to go on and on forever. 1, 2, 3. I'm just going to approximate that at 2.2. So at 2.2. So we'll do over 3, 2.2. All right. And again, this is approximation of the point. But you can see my graph is going to look something like that, where my asymptote for the parent graph is going to be x equals 0, where my domain is from 0 to infinity, and my range is going to be from negative infinity to infinity. OK, so now what we're going to do is we need to apply these transformations. And it tells us to reflect the x-axis and then to shift the graph up 4. So when we're applying this, we need to reflect the x-axis. So therefore, this graph is going to be reflected about the x-axis. So instead of going over 3 up 2, I'm going to go over 3 down negative 2. So it'd be 3, negative 2.2. Now this point's going to remain the same, because when you reflect it over the y-axis, it's now going to be changed. Then I need to add 4. Well, if I'm now at 3, negative 2.2, if I shift this up 4, well, let's take a look at this first point. If I take 1, 0 and shift that up 4, it's now going to be over 1, up 4. 1, 2, 3, 4. And then this point, if I shift it over, it's still going to be over 3. But now if I add 4 to negative 2.2, right? Now what that's going to do is that's going to take me back up to, let's see here, so that'd be 2.2. So if you go up 1, it'd be negative 1.2. Take it up again, take it up 2 units, that'd be at negative 0.2. Go up another one, now you're at point over 2, so now you're at 0.18. 2.2, or 0.02, now you're at 0.08, and then at 1.8. So now it'd be at over 1, up 1.8. So let's go ahead and, so this point is now going to be at 5, comma 1. No, I'm sorry, 1, comma 5. Right? And then this graph, if you do negative, and if you even look at this, just to go and confirm, if you do negative 2.2 plus 4 is now going to be 1.8. So this point is now going to be at 3, 3, comma 1.8. All right? And again, my graph is reflecting, so it's going to be in that formation of the red. All right? So now I need to go and take a look at it and see, well, what exactly is my asymptote? Well, my asymptote hasn't changed, so my asymptote is x equals 0. My domain, just with the reflection over the x-axis, is not going to change. So my domain is still from x to infinity, and my range is now also going to be from negative infinity to infinity. So there you go, ladies and gentlemen. That's how you graph a natural logarithmic equation when you have a reflection over the x-axis and a shift, a vertical shift. Thanks. Again, we need to identify all the transformations. So again, you can look at it and say, well, what is my trigonometric function? That's the log of x function. All right? So I'm just going to identify the transformations from left to right. The first thing I notice is I'm multiplying by a negative. Am I multiplying by the negative outside or inside of that log of x? Outside. So therefore, it's a reflect x-axis. OK? You can see now I have a 1/3. I'm multiplying the 1/3 outside the function. So therefore, it's vertical. It's less than 1, so it's a vertical compression. And you can just write vertical compression of 1/3. Then I now enter inside the parentheses of the function, and notice I'm subtracting a 2. So it's inside the function. That means it's a horizontal shift. Since it's minus 2, I'm going to be going right 2. OK? So in this example, again, guys, to graph this, we need to make sure we know how to graph the natural logarithm. Again, guys, it doesn't matter what the base is. If you guys remember when we looked at Desmos, the base just tells you how sharp it still crosses, right? But it still crosses at 1, 0. So the graph looks something like that. OK? Well, now we just need to look at what's our only transformation. Our only transformation is x minus 1, which is telling us to shift the graph to the right 1. So now I'm going to shift my x-intercept over 1. However, remember, there is a vertical asymptote. So if I'm shifting my graph over 1, the asymptote also needs to be shifted over 1. So now the graph looks like this. And it now has a new x-intercept at 2, 0. However, also remember, it's being reflected about the x-axis, right? So I kind of got ahead of myself. And I now need to reflect it about there. So the blue graph will be what your graph would look like. Does everybody see why it's negative? That reflects it. And then the minus 1 shifts it to the right. What? The red graph is me just doing the transformation to the right. But then I had to reflect it at the end. So now let's go and answer the questions. Graph the function, analyze the domain. The domain is the set of all x values. How far to the left does this blue graph go? How far does the left go?
0.
1. Right? Remember, that's the new asymptote, right? So 1. How far does it go to the right? Infinity. The range. And remember, it doesn't touch 1. So therefore, y, that's right. The range, how low does this graph go? Negative infinity. How high does it go? Positive infinity. Next thing is they say continuity. That is continuous on all events. Increasing or decreasing. From 1 to infinity, the graph is decreasing. So you could just say from the interval 1 to infinity, it's decreasing. Boundness, this graph is not bounded at all. Extrema, there is no extrema. Symmetry, it is not symmetrical about anything. Asymptotes, you can say that the asymptotes are at x equals 1, because remember we shifted the whole graph to the right. Originally the asymptote was at 0, so when you shift it over to the right. And then end behavior. Well, here you guys can see that as we're going to the left, as x approaches, we're not going to negative infinity. So as approaches x equals 1, so as the graph approaches graph's 1, you can say f of x approaches infinity. And as x approaches infinity, f of x approaches negative infinity. OK? And then that's it. Welcome. All right, so what I have here is y equals log. Now, again, if we don't write the base, we know it's going to be base 10. So log base 10 of negative x minus 1. So when we look at this, we see that negative x, we know we're going to be reflecting the y-axis. And the minus 1 is going to tell us to shift the graph to the right, 1 unit right. OK, so again, to graph this, we want to graph the parent function and then apply the transformations. So the parent function in this case is going to be y equals log of x. And then we'll go and graph our final equation. All right, so in graphing our parent graph, again, we can just go and again just choose some values that we like to for our x and our y. All right, so again, if I go ahead and choose x equals 1, we know y is going to have to equal 0, right? Because 10 raised to what power is going to equal 1? Well, we know y would equal 0. And again, a lot of times I can rewrite this in exponential form, so it kind of maybe make a little sense for me. So if I was going to look at this, I'd say 10 raised to what power is going to equal x. And a lot of times I always like to choose x equals 10 as well. So therefore, we know y would equal 1. So I can plot my 2 points at 1, 0, and then at 10, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up 1. So therefore, my graph's going to look something like this. And in there, I know that I have an asymptote at x equals 0. I have a domain that goes from 0 to infinity. And I have a range that goes from negative infinity to infinity. All right? So now what we need to do is, what we're going to do is, I need to apply these transformations. And what the transformations are going to tell us to do is to shift the graph 1 unit to the left, and then what we're going to do is reflect. And so there's a couple things you can always do when you want to go ahead and graph these, is you can go ahead and take a look at your log and just go and plug it in with there, but you don't need to always go ahead and look at that, because what you can do is when you're applying this, just take your points, all right? And I'm sorry, I kind of missed one direction, but take your points and then reflect them. So if I actually just apply my reflection, shift it over first, then reflect, yeah. So if I take my reflection and reflect the y-axis, so here's my point at 1, 0. If I reflect this, it's going to be reflect over the y-axis. Instead of going over 1, I'm now going to go to the left one. So then I have a negative 1, 0. And then instead of having 10, 1, that's now going to be at negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over 10, positive 1. So now my graph's going to look something like this, right? And then I need to shift it 1 more unit to the left. So therefore, what am I doing? That's 1, 0. So it's up there, right? OK. That's at negative 1, 0. Then what I'm going to do is now shift this graph over 1 unit to the left. So therefore, that instead of it being negative 10, 1, now my point is going to be at negative 11, 1. Instead of negative 1, 0, now my y-intercept is going to be at negative 2, 0. All right, now, since I've shifted the graph 1 unit to the left, my asymptote that was at x equals 0 is now at x equals -1. And that's going to change, that's going to affect our domain and range. Because if my asymptote now is at x equals -1, that means my domain is now from -infinity to -1. And my range is still going to be the same of -infinity to infinity. So there you go, ladies and gentlemen. That is how you graph a logarithmic equation with a y-axis reflection and a shift 1 unit to the left. Thanks. OK, so on this next, what I'm asking you to do is to graph, identify the domain, the range, the asymptotes, and the transformations. So when graphing logarithmic functions, I think the main important thing is to at least know what the parent graph looks like. The parent graph has an x-intercept at 1, has a vertical asymptote at 0, and looks something like this. OK? So now we just need to apply the transformations. So this 2 is going to be our vertical stretch. That is going to be vertically stretching our graph. We're going to have the -3, which is going to be shifting our graph 3 units to the right. So here's my x-intercept. I can move my x-intercept 3 units to the right. 1, 2, 3. And then this 1 is going to be up 1 unit. Right? And then the 2, remember, is vertically stretching your graph. So it's going to look maybe something like that. I originally have an asymptote at x equals 0. So if I'm shifting my graph 3 units to the right, that means my asymptote is going to be shifting 3 units to the right. Now, by looking at the graph, this blue graph, I can identify what is my domain, my range, and so forth. So my domain is going to be from 3. It's at an asymptote, so it's not going to contain it. So 3 to infinity. My range, you can see that the graph is going down to infinity, and it's going to continue increasing, so it's going to go up to infinity. That's going to be at -infinity to infinity. My vertical asymptote for the parent graph was at 0, and that got shifted over 3. So that is a vertical asymptote at x equals 3. And the transformations, I forgot to do that. So transformations is a vertical stretch, factor of 3. We're going to do shift 3 units right, 1 unit, or shift 3 units right, 1 unit up. And there you go, ladies and gentlemen. That is how you graph logarithmic functions with transformations. Thanks. Ha-ha! So here we go. All right, so now in this case, I have y equals 1/2 log base 6 of x minus 4 plus 2. And whenever I'm looking at a problem like this, I always wanted to kind of determine what are exactly my transformations. How am I shifting this graph from its original parent graph? Well, the x minus 4 is going to tell me I'm going to shift my graph 4 units to the right. And then the plus 2 is going to tell me to shift my graph 2 units up. All right? So what I need to do is, what am I shifting 4 units to the right and 2 units up from? So to do that, we want to graph our parent function. All right? And we also, then here is going to be our final graph. So our parent function, again, we're just going to take this without the transformations, would be y equals 1/2 log base 6 of x. Now, you can do it without the 1/2, and then just take those points and multiply them by your x values by 1/2 if you want to. But I like to leave this in here because when I rewrite this in exponential form, what I like to do is divide by 1/2. So therefore, it's 2y equals log base 6 of x. Then when I rewrite this in exponential form, I have 6 raised to the 2y equals x. All right? And again, you can graph the parent function without the 1/2 and then just multiply each of those points. But then again, you're just doing more and more dilations, which I like to kind of get it out of the way. So now what I want to do is create a table of values for this graph. So I'll have my x and my y's. And a lot of times, again, what I like to do when I'm choosing my x values is I want to choose when is x going to equal 1 and when is x going to equal the base of 6. So x equals 1, obviously, when 6 is raised to a power of 0. 6 is going to be raised to a power of 0 when y equals 0. Then I need to look at, well, when is x going to equal 6? That means this is going to be raised to a power of 1. Well, 2 times 1 is going to leave me with 1/2. So when y equals 1/2, 1/2 times 2 is 1. 6 raised to the first power is just going to equal 6. So now I have these 2 coordinate points that I'm going to want to graph. 1, 0, and then 6, 1/2. So 1, 2, 3, 4, 5, 6. up 1/2. So therefore, my graph's going to look something like this. It's going to have a very, very sharp turn. When looking at my, my graph, I know that my asymptote is at x equals 0. My domain is from 0 to infinity. And my range is from -infinity to infinity. All right? And that's just the basis of understanding what the parent graph is going to be looking like. But just notice on this graph it has a very, very sharp turn. But the main important thing what I want to do is take these points. And what I'm going to do now is now transfer these 4 units to the right. So instead of dealing with the point 1, 0, I'm now going to deal with the point 5, 0. 1, 2, 3, 4, 5. And instead of dealing with the point 6, 1/2, I'm now going to deal with a point 10, 1/2. So 5, 6, 7, 8, 9, 10. But now, instead, I'm not going to be shifting them now, or 6, 1/2. But now what's going to happen is I'm going to shift this graph also 2 units up. So let's say here's 1, here's 2. So therefore, and there would be 3. So up 2 would be now instead of at 0, now it's up to 2. And it started at 1/2, it's now going to be at 2.5. All right, now the next thing what I always like to do is draw the asymptote first. My asymptote was originally at x equals 0. That asymptote has now been moved to x equals 4. 1, 2, 3, 4. Because the graph was shifted 4 units to the right. All right, so now I can graph this. And you can see it has this very, very sharp turn. And my 2 points, again, are 5, 2, and now 10, 2.5. All right? But now we need to understand that our domain and range and asymptote have changed. Our asymptote is no longer at x equals 0. It was shifted 4 units to the right. So when I say my asymptote, now I can say x equals 4. My domain is from my asymptote to infinity. So that's going to be at from 4 to infinity. And my range, however, even though I shift it up or down, you can see that this graph is going to continue to rise and continue to fall. So my range is from -infinity to infinity. So there you go, ladies and gentlemen. That is a brief example on how to graph logarithmic functions equations. Thanks. OK, welcome. Here what I have is y equals negative log base 5 of x plus 1 minus 3. So we have a lot of different transformations here, right? So I'm going to want to write these down. That's always the first thing I like to do when I have multiple transformations. So I have my function being multiplied by a negative. So therefore, that's going to tell me to reflect the x-axis. I also have an x plus 1, so I'm adding inside the function. So that's going to, or inside my equation, I guess you say. So therefore, that's going to shift 1 unit left. And then I have a minus 3. That's going to tell me to shift my graph down 3. OK? So we have a lot of different transformations. And you can do these all on your own. It kind of really depends on how comfortable you feel with graphing and applying your transformations. What I always like to do, again, as I go back through this, is just creating our parent graph first and then applying our transformations. So we can apply our transformations in a couple different steps if we want to. And why not? And then maybe I'll do the last. I'll do maybe the reflection, and then I'll do the last 2 at the end. All right. So you don't need to do this 3 times. You can obviously cut some steps, but I want to break it down for you so then you'll get an idea of how we're going to go about this. So the first thing I always like to graph is my parent function with no transformations. This is going to give me some points that I can use to then apply my transformations to. So I have a logarithmic equation. I really like to write that in exponential form. So 5 raised to the y equals x. Therefore, I can now create a table of values that I can plot my initial graph. So I'll say x equals y. And when I'm choosing my points for y, I want to choose points that are going to make x equal 1 and x equal the base of my exponent. So here if I have 1, y has to therefore go ahead and be 0. And if x equals 5, then we know y equals 1. So therefore, I have the point 1, 0, which from the parent graph we should recognize as the x-intercept. And then we have the point 5, 1. 1, 2, 3, 4, 5, up 1. All right? Now, so we have a graph that looks like this. Does not touch here. All right? So we have a graph that's going to look like here, look like this. And now the next thing is, let's go and say we're going to reflect the x-axis. So what does reflecting the x-axis look like? Well, I don't know, x-axis. So what that means is we're going to take this graph and now reflect it over the x-axis. So instead of going over 5, 1, 1, 2, 3, 4, 5, instead of going over 5, up 1, now we're going to go over 5, down 1. All right? And if we reflect the point 1, comma 0, since that's on the axis, that's not going to change. So now my graph is going to look something like this. All right? So that's a reflection of my x-axis. But then there's two other transformations that need to happen. The next thing is I need to take that graph and I need to shift it now down 3 units. And I also need to shift that graph. I also need to shift that graph 1 unit to the left. So what I'm going to do is I'm going to take these points and I'm going to shift it 1 unit to the left. That's at 1, comma 0. So therefore, now it's going to be at 0, comma 0. And then if I shift it down 3 units, that's now going to be at 1, 2, 3. If I take the point 5, negative 1, I shift it 1 unit to the left. That's now going to be at 4, 1, 2, 3, 4. And then if I shift it down 3 units from negative 1, that will now be at negative 4. So 1, 2, 3, 4. So that will now be at negative 1, negative 4, negative 4. And then this point is, again, shifted 1, so it would be at 0, negative 3. Perfect. All right, then the next important thing is I need to look at this asymptote. Remember, we have an asymptote here at x equals 0. So if I shift my graph 1 unit to the left, I now have a new asymptote at negative 1, because it was originally at 0. But since I'm shifting my graph 1 unit to the left, my asymptote is now at negative 1. So by shifting this over, my graph is going to look something like this. All right, and now to determine our asymptote, we want to write in, or determine our domain and range, we want to remember that our asymptote is at x equals negative 1. Therefore, the domain is going to be the set of all x values that we can evaluate for this function. So that's going to be from all the values of negative 1 to infinity. And our range, since a logarithmic graph increases to infinity and decreases to negative infinity, our range is going to be from negative infinity to infinity. So there you go, ladies and gentlemen. That is how you graph a logarithmic equation, or function would be the same process with using multiple transformations. Thanks. All right, so in this example, they want us to graph. So what I asked you guys to do, just like your exponential homework, was to sketch the graph of the original and then the transformation, and to provide me a point. It's 2 log? OK. So first of all, let's just graph what the normal logarithmic graph looks like. It crosses at 0, comma 1, and just looks something like this. Oh, I'm sorry, it crosses at 1, comma 0. Correct? Yes? OK. The next thing. Now, what I typically prefer to do is to rewrite this as log of negative x plus 3 minus 1. OK? So now what you guys can see is my graph has now been, so remember A, that's just going to be your vertical stretching and compressing of the graph. That's actually not going to affect like the intercept. But what that is going to do is that's just going to kind of stretch the graph in on there. You guys could also look at, we have this negative, or remember the only thing though that when that A is negative is that it's going to reflect about the x-axis, but since that's positive, we don't need to do that. And then also we have the plus 3, which is going to be shifting the graph to the left. We have this negative x, which is going to reflect it about the y-axis. And then we have the minus 1. OK? Now, where a lot of times this gets tricky is when you have a negative. When you have a negative inside of this, what we can do is, again, rewrite this one more time. When you just have one negative, that's not really a big deal. But if you factor that out, you can see that's actually being multiplied, that negative is actually being multiplied, but that's actually shifting it over to the right. And so you're actually not actually shifting it to the left. And that's why I just wanted to make sure if I remembered it correctly. If you guys go ahead and plug that into your calculator, you guys can see that that gets verified in the graph. It's actually being shifted. It's actually going right, because what you do is if you factor that negative, you're really multiplying the inside by a negative. It's not just the x. So therefore, you'd want to factor that out. And now you can see that the graph is being shifted. Just put it on my desk. So it's being reflected, telling you to shift it to the right 3. 1, 2, 3. And then it's going down 1. So my new point on my graph Roman that I have is 1, 2, 3, 4, down -1. It's also important to understand that my asymptote is now going to be 1 over from here. Okay, because remember that was my x-intercept. So my asymptote is going to be 1 over. Since this got reflected, it's going to be 1 over to the right. And so my graph would look something like this. Okay. Welcome. Okay, so ladies and gentlemen, so what I'm going to do is show you how to graph y equals -ln of -x plus 2. So I like to go ahead and write down what our transformations are going to be, and then we'll graph the parent graph and then the transformations. So in this case, I have a -1 being multiplied by my function, so that's going to tell me to reflect the x-axis. I have a -1 being multiplied by my x inside the function, so that's going to tell me to reflect the y-axis. And then I have a +2, which is going to tell me to shift 2 units left. All right. So now what I like to do is, again, graph my parent graph to make sure that I have everything correct. All right. Now, when looking at my parent graph, again, all I simply want to do is just graph the parent graph with no transformations or reflections. Then what we'll do is we'll apply our transformations to our problem. OK, so the first thing that we're going to do is ln of x. Now, we can just go ahead and, again, determine points for this. You guys can just plug in points. We know that if I chose 1, then ln of 1 is going to be when y equals 0. So that's the first point. And that just comes in just graphing the parent graph. I'm not multiplying it by a multiplier. So therefore, your y-intercept, or x-intercept, I'm sorry, is going to be 1. Then you can choose another point. Remember, we're just choosing an xy table. So when doing an xy table for this, you can just pick whatever points you want. 1, and let's just pick 3. So if I did the ln of 3, I'll just plug that in my calculator. ln of 3 is 1.98. So I'm just going to leave that as 0. And then 3 would be 1.1. All right, and again, this is an approximation because e is an irrational number. So over 3, 1, 2, 3, and then instead of up 1, it'll be like just over 1. All right, so my graph's going to look something like this. And here we are, again, remember from the parent graph, we have my asymptote is x equals 0. The domain is from 0 to infinity. And the range is from -infinity to infinity. And that's for my parent graph. And that's going to pretty much be unchanged unless we're multiplying it by some multipliers, either inside our function or outside of our function, meaning some numbers that we're going to multiply by. However, the domain, range, and asymptote aren't going to change. Really, your 2 points would be the only ones that are going to be affected. All right, so now we have these transformations. So the first transformation that I'm going to want to apply before I do my reflections is I'm going to want to apply my shift left 2. So currently, I have 2 points, 3, 1.1. All right. So if I shift this graph over two units to the left, I'm now going to have a new point at -1, 0. And I'll also have at 1, 1.1. All right, so now, and then my asymptote also, instead of being at 0, it would now be at -2. So if I was going to graph this graph, it would look something like that. But now, ladies and gentlemen, we have two reflections. I'm now going to take this graph and reflect it over my y-axis. So then, at -1, reflected over the y-axis, again, is going to take me back over to 1, 0. And let's actually do this in a different color. And then at 1, -1.1, if I reflect this over the at y-axis, now that's going to become -1, 1.1. And my asymptote, instead of being at -2, is going to now be at +2. So you can see the graph is now going to look like that, and you can see how it is. Really, this would be the same point. Maybe it looks something better like that. All right, so now the graph has been reflected over the y-axis, but now I need to reflect it over the x-axis. So if this point is at -1, 1.1, now it needs to go down to -1, -1.1. So then this point, though, is still going to remain the same. And now my final graph is going to look something like that. So again, here's my original graph. I took this graph and I shifted it left 2, which gives me this graph. Then I take the blue and reflect it over the y-axis, which gives me this graph. Then I reflect it over the x-axis, which now gives me that graph. So when looking at it, now what we want to make sure we do is just eliminate these graphs that we used to help us graph our original function. And then what we can do is kind of determine what is going to be our domain and range and so forth. All right, so we don't have this asymptote anymore. All right, so now you can see my domain is going to go all the way over to this asymptote, which remember now is at 2. So my asymptote is now at x equals 2. So therefore my domain is from -infinity to +2. And my range, this graph still is going to increase indefinitely to infinity and to -infinity. So my range is still going to be from -infinity to infinity. So there you go, ladies and gentlemen. That is how you graph a natural logarithm with two reflections and a horizontal shift. Thanks.